All right, so let's consider ourselves a differential equation. Consider p0 of x, y double prime, plus p1 of x, y prime, plus p2 of x, y is 0. Okay? This is, so I can do a little bit more general thing, but this is a good spot to start. So the thing I'm doing here is my p0, p1, and p2 are going to be polynomials. And I'm also going to assume that they are without common factors. Why would I assume that?
Because you could simplify it to where you don't have it.
Yeah, basically you could divide through by that common factor and plug that hole in this thing, in this differential equation, essentially. Right, it's just happening at a point, you could get rid of it, essentially. You guys all good with that? Does everybody understand what I mean by common factors? Yeah? Okay.
So if, say we did that, you might end up with a rational function. Does that include, does polynomials include like x minus 1 over x minus 2?
So if they all have a common factor, right, and you divide through by the common factor, you'll be plugging a hole in each of those kind of rational functions by simplifying. And in the end, you won't have a rational function. You'll
But if
still
only
have
two of
polynomials.
them share.
But if only two of them share, then they don't all share a common factor.
Oh, okay.
Maybe that language makes things more clear. Without a common factor between all three. Let's cool that. Okay. I need a definition. So, an ordinary point, and I'm going to call this something like star, of star is any x naught with p of x naught, p naught of x naught is not 0. There were way too many knots in that sentence. So an ordinary point is one where this leading polynomial isn't 0. In other words, it's a point where you honest to God have a second degree differential equation. Right? Because if you look at a point where that initial p naught function is 0, then really you don't have star. You have some truncated first degree version of star, and that would be weird. Right? So I'm only going to explore ordinary points. I am going to say something about the opposite of an ordinary point. So I'm going to put that definition up here too. A singular point is any point which is not ordinary. In other words, the singular points are what?
Holes?
Kind of, yeah. There's spots where you're not looking at a second degree differential equation, right?
They're like the boundaries of the...
Yeah, they're going to be kind of the boundaries of solvability for me. Really, they're just the zeros of p0, right? So you just, to find the singular points, you take the p0 polynomial, you set it equal to 0 and solve, and those are your problem spots. You guys good with that? Okay. And my claim is that I'm going to be able to solve this thing. So, little theorem. So my little theorem is we can solve star around an ordinary point x naught with y equals the sum from n is 0 to infinity of an x minus x naught to the n In other words, I can guess a power series solution and make that work at any ordinary point. And the radius of convergence of y, being that power series, will be at least the distance from x naught to the nearest singular point. In other words, you've got a number line, right? Number line? Some places your x naught lives over here. You went out like an enterprising person and found all the zeros of p naught. Right? All 37 of them or whatever. And then you wonder, what's the best I can do in terms of finding a radius for y? Like, in other words, how good's my solution, right? I'm going to find this power series solution. Like, that's not actually super hard. Computer that crap. Or sometimes you get lucky and you can see them. But you find some way to get a power series solution. Where's that thing going to be good? It's going to be good on an interval that's at least the distance from x naught to the nearest singular point. Might be better. But at the very least, you know it's good for in here.
If we have a point like, I see how there's the one on the left that's closest and the one on the right. Can we make that conclusion, or is that not valid?
No, it's got to be the closest one.
Okay.
But we still might be actually okay so that, like, if we push that left boundary, or, like, our interval could extend all the way to the,
Yeah, we might be good past
but
that.
we just don't know for sure.
Like, you might well be able to extend over a singular point.
You can just
It's not
guarantee-
necessarily true. And also it should be noted that the singular points really should live in the complex plane. So if there's a singular point in the complex plane off over here, you should consider that one too. So it's not quite as easy as the like, because you got to consider the complex pairs too.
Does that mean our radius would make a circle in the complex plane? Like, would we go up that distance?
Yeah, you'd go. So discard that for a bit. Cool. All right. So good. This is the thing I need. Now let's try to use it.